Now in this presentation, I'm going to use all the concepts Puya explained about the curves and application profiling to do performance prediction. So we use all this to predict application performance. And the outline of this, so I will start with the story of PROFET, general idea, general workflow, talking about system profiling, application profiling, putting everything together to do the application profiling, some evaluation, so I will show you where we evaluated, this brutal evaluation we did with PROFET, and the last thing, the demo and hands-on on how to use it, what you can do with PROFET, using real examples, real Mare Nostrum data that you can access, you can have it. And so to start this story, we need to go back to 2014, where in the memory team, there is this project that the objective was memory design space exploration. So considering the target CPUs, the high-end Intel CPUs, so we have the same CPU, but we want to evaluate different memory technologies, so different main memory. This is the objective of this. And I think right now in this moment, you already know that we have a bunch of different memory technologies that we can have. So for example, HBM, MRDIMMs, CXL memory expanders, they are all here for us. Some of them are already in Mare Nostrum, so we can use it. And one interesting thing about these technologies is that they are not completely replacing DDR. So in a lot of systems, and I will show some real examples, they are together with DDR. So in this first one, we have Intel Max with HBM, and in the same CPU, we have HBM and DDR. And this is the example we have in Mare Nostrum. So in the partition with HBM, some of the nodes have HBM and DDR in the same CPU. And another example is we have DDR and CXL memory expanders in the same CPU. So this is something, it's happening, it's real, and the current approach to evaluate this is to use hardware simulators. So using a CPU simulators together with a memory one like ZSIM, DRAM SIM, this is the current approach. But there are some problems related to this. And let's see if these problems happen in this room or not. Have anyone here used hardware simulators? Please raise your hand. How was it to use it? Was it completely easy, super fast to learn it? Was it hard, more or less? More or less. I'm seeing the faces and the hands like shaking, saying, yeah, it was hard. And I used hardware simulators during my master too, and it was pain, agony, and torture. It was really hard in the beginning. Later, I got used to it, but it's really hard to use. And apart from this frustration of using, it's time consuming. So it's not about you run and you have your result. You run and you wait. And you wait and you wait and you wait. And the next day, the next week, you have your results. And if everything is okay, you have it. If not, you need to run again. So this is the problem with hardware simulation. So the idea here is maybe we can do this in a different way. Maybe we can have a different approach to this. And this approach needs to reply the question of how would my performance, energy, power change if I change the main memory? So if in the same CPU I change the main memory, I put on the same slot MRDIMMs now, how much would my performance change? Would it worth to change to MRDIMMs, for example? So that's the question we want to answer. And the idea of PROFET is we profile an application on this baseline system, something you can access, something you have it, Mare Nostrum, for example. So you profile the system, the system profiling plus the application profiling, and you have a target system. So a new memory technology a different node in Mare Nostrum. So we'll have something different that the memory will be different. So the CPU is the same, but I want to check a different memory in that same CPU. And here we can have, for example, as a baseline, the general purpose and the target, the one with more memory, the high memory one. Or we can have RDIMMs and MRDIMMs. So these are scenarios we can explore. And PROFET was this first tool developed by the BSC Memory Team. And it was already used by various industrial partners. So Samsung, Micron, Huawei. And another interesting thing about PROFET is that it was first developed for SandBridge with DDR3. And now we are using the same tool for HBM, for MRDIMMs, for CXL memory expanders. So it really passed the test of time. And another curiosity is that if you check the date, the year of the publication of PROFET, it was published in 2019, so before MES. So PROFET was published, and then it leads to the development of MES framework. So have MES as a benchmark to profile the system. And now going to how it works. This is the overall workflow. So most of the things here you guys already know about. So we have the first input of this model as the bandwidth latency curves, so my system profiling. The second one is the CPU parameters. This one is easy. We don't need to worry much about it. Are just some numbers that are not hard to get. And the third one, the application profiling. So this one is also the same thing that Puya explained will apply to this. I will go over it again, but it's the same thing. It's the same explanation. And now these three inputs goes to the performance model. The performance model, we use all the inputs and will give you the performance estimation. So now I will go over the inputs, the performance model, and the outputs you can get using PROFET. So the first thing, the curves. So as I mentioned, we need a baseline system. So one family, of course, will be your baseline, something you have access, something you can measure. So any existing memory systems. So for example, here we can have direct the DDR4, 5. So Mare Nostrum, for example. So this is one family of curves. And then you have the target system. So one more family of curves. And this target system will be any memory systems where you can measure your curves. Any memory system you want to evaluate and you can get the curves from. And you can get the curves from measuring the curves in your system that you have access. You can get it measured on boards and prototypes. You can get as a detailed manufacturer simulation. You can get it from sensitivity analysis, which means we can do sensitivity analysis to simulate if this curve, my baseline, would have 10% less latency or 20% more bandwidth. This is the sensitivity analysis, and this is thanks to Claudia, who is here, who made this in the TFG. And this is the first input for PROFET. So nothing new here. We are getting the curves using MES benchmark. So these are the curves. This is one way of getting them. We need to have the curves. You can get them from different ways. But the curves I'm showing here are obtained using MES simulator. And the second input are the CPU parameters. So here we are talking about 4 CPU parameters we need for the model. So we have the reorder buffer capacity. We have misinformation status holding register capacity. We have the minimum theoretical cycles per instructions, the CPI, and the latency of the last level cache. So most of the parameters you can get from vendor spreadsheets, for example, or for some of them you can measure. So you can measure the latency of the last level cache using a pointer chase, for example. You can measure some of them, and the others you can find on documentation. And the format of the file you use for PROFET is similar to this one. So it's a JSON file with the label of each of the parameters and the value. So if you want to use PROFET, you can copy this structure and changing the values according to your system. And the third and last input are the application profiling. So the application profiling, since we are talking about prediction, we will do this only on the baseline system. So if I want to evaluate, and I will show this on the demo, if I want to evaluate my performance, if I run it on the high mem nodes, I don't need to run there. I will profile on the baseline, and I will predict my performance on this different memory system. And so it's the same explanation that Puya gave. So we execute the application on these baseline systems, and we read the hardware counters. Apart from reads and writes, that is what the mass benchmark measures, we need CPU cycles, number of instructions, and number of last level cache misses. In terms of hardware counters, these are not exotic hardware counters. They are easy to use. They are well documented, more or less. Considering hardware counters, they are. And you do this in samplings of time. So you have the sampling 1, 2, and so far so on during the entire execution of your application. And you can select a reasonable sampling interval. So PROFET, you need the samplings. You can choose the sampling interval you need, ideally bigger than 10 milliseconds. And with all this, we can do the first step, which is I can position application on the curves. Same way the Puya and Victor was explaining, we can do this on the baseline system because it's where we are profiling our application. So this is the same example. So baseline curve in blue and target curve in green. And we can put all the dots, all the observations of my run in this baseline curve. So this is everything you need to run PROFET. So we have now the curves, the CPU parameters, and the application profiling. So now we talk about the model. This is only one example to illustrate, but this can get much more, not complex, but with applications that goes all over the curve. So this is another example with applications going all over the curve. And now we talk about the model. So the idea here is an unconventional approach to this, to do this memory design exploration, which is model this problem, model this prediction as a system of equations. So PROFET is a model. If you check the code, we have equation after equation. And the idea of the model is we solve this equation. So we will solve this equation for each of the observations you saw, each dot of the profiling of the application. We'll solve this equation, and in the end, the result of this equation will give us the performance change, the performance of my application in this new memory system. And here we have a lot of the equations. I will not enter in details about the equations. If you want to go over them, you can check the paper. And also in the code, in the GitHub, the equations we have in the code are named and with comments to link to the paper. So if you read the paper, you check the number of equations, you'll find them in the code. So you can go over the code and the paper at the same time. And what is the main idea of this system of equations? First idea is we can position the dots on top of the curves. So we can do this, considering that I have curves that are my system profiling, and I'm covering all the space of that system profiling, my dots will be somewhere on that curve, considering the read ratio of the dot, considering the bandwidth, but my dot will be somewhere on that baseline curves. And the second idea is that, okay, I have my dots on my baseline system, and now the idea is, if I have the system profiling of my target system, my target memory, I can move from baseline to target because my dot will be somewhere on my target curves too. So I can move from this to my target curve. And this is the main idea of PROFET, moving from one curve to another. So we predict where that dot would be on the target family of curves. And in the end, you have all the dots that you profiled in this system predict in the other system. So you profile everything baseline, and PROFET will predict on target system. So this is the first output you can get from PROFET. Again, this is one example. And you can have also the numbers themselves, not only the view of this, but you can have the performance in terms of IPC, in terms of CPI. So IPC are instructions per cycle, and CPI is cycles per instructions. And also you can have it for bandwidth, for latency. So you have this view of where are my dots, and you also have the numbers themselves that you can compare. And this is another example. So all the dots here are predicted. So you measure in this baseline and you predict in the target system. And I explained how it works, but how we know this is correct, how we know that we can trust this tool. And for this, we have a brutal evaluation in a lot of different systems. So here we have results for SandBridge with DDR3, changing the frequency of the memory. We have results for Knights Landing, DDR4 and MEC run. We have Huawei Kunpeng, DDR4 different frequencies. Cascade Lake with DDR4 Optane, DDR4 changing the frequency, DDR4 Optane. We have Emerald Rapids changing frequency, Granite Rapids from RDIMMs to MRDIMMs, and now we are working on DDR5 HBM and DDR5 to CXL memory expanders. So we have all this brutal evaluation in a lot of different systems, and we measured the error. So we ran the same application on this target memory system, and we checked, okay, how is my real performance and the predicted one. So we measured the error, and you see that for most of them, the error is below 5%, which when we compare to simulators that have a higher error, this is good. So this is the evaluation. And now, one example of things that you can do analysis, you can do it with PROFET. We have the examples of RDIMMs to MRDIMMs. So as Puya was saying, Peter was also talking about MRDIMMs. It's amazing new memory system. So the performance is, the bandwidth is increasing, the latency is almost the same or a little bit lower. So we have this amazing memory, and it's just a matter of plugging in your system and you can use it. So these are the MRDIMMs, and one analysis that we made about the MRDIMMs using PROFET is, okay, let's do this for a lot of different benchmarks. So we have here latency ones, so Google Multi-Chase, Intel MLC, Google Multi-Load, this stream. So we have a lot of different benchmarks. And we have here this chart that is one output from PROFET that you can get. So if you run with multiple applications, PROFET will give you this chart. And here we have the different applications, the different benchmarks, and the performance different in the y-axis. So we see the gray bar as the predicted performance. So gray bar is your predicted, and we have some error bars in the gray bars that are related to some boundaries that we cannot measure. So we have some boundaries in this system of equations that we cannot measure, so we bound them. That's why we have the error bars. And the red diamond here is the measured one. So the measured performance different from RDIMMs to MRDIMMs. So we see that for most of them, we are really close to the reality, really close to what we measured in real hardware. And also we can have the charts with the applications plotted on top of the curves. So we have baseline as your blue curves and target as your green curves. So RDIMMs and MRDIMMs, and here we have a latency one. So it's really in the beginning of the curve. So it's Intel MLC. HPCG, so spread all over the curve, and also string copy that is here in this part. So you have profiled in baseline and predicting the target family of curves. Everything I explained here now was about performance, but PROFET is not only about performance, it also can do power and energy prediction. I will not talk about this right now, we can talk during the lunch break. And it's just to show you guys that it's not only about performance, we can do energy and power too. And last thing before the demo, so a group of why this is cool, why we like, why we use this tool is it's a disruptive approach for this. So we are not using simulators here for anything. We don't use simulators to measure, we don't use simulators for any step in the process. We really measure your hardware. It's really measured in your hardware, measure the application running in your hardware, and then we do the prediction based on the equations, based on the CPU parameters. So there is no hardware simulator in this process. Also, it's fast. So you see in the demo that we have the results in not even seconds. It's really fast. So imagine if I wanted to do a demo about simulators. We would need to put it here, go for lunch, and if you are lucky, maybe we would have it after lunch, or no, probably not. So it's really fast. And as I mentioned, it was designed for SandBridge, and now I will show results for MRDIMMs, for example. So it's a tool that really passed this test of time, that it's really well modeled the equations. And it was brutally evaluated in a lot of different actual hardwares, and we are still evaluating in new ones, so CXL memory expanders, HBM, and that's it. So before the demo, any questions now about this? No? Okay. So the demo, I will use the same benchmark, the same apps as the MES one. So it's Stream, so the kernel triad of Stream, and Google Multi-Chase. So we have two examples, one in the lead off part of the curve, one in the beginning, which is latency, and one in the end of the curve. And I will do the demo considering Mariana 5 in the GPP partition, so normal one, the one we normally use, and I will do the prediction on Mariana 5 GPP high mem. So we saw the dots, where would my application be on that other curve, but for this demo, we don't need to run our application on that different node. We will predict the performance. And we will predict the performance. It's not only the visualization of where it would be in the curves, it's really, let's predict this. and one more demo about RDIMMs to MRDIMMs. So let's see how would this extra bandwidth would impact the performance of my applications. So we have the QR code here and also the link if you want to download the materials, the visualizer, they are all in this link. So as I was saying, I will start with Mariana 5 GPP to HiMem and then RDIMMs to MRDIMMs. So let's see it. I will open the visualizer now. Okay, so if you download and open the visualizer, this is what you are going to see. So we have here the three inputs I was explaining. So we have the curves. So baseline curve here, target curve here. We have apps, and if I go down, we have also the configuration. So the CPU parameters will be here. So it's really only about these three inputs: curves, application profiling, and the CPU parameters. And then we will see the curves in that part. So now let me open the first input, so the curves. Thanks. So here I have the data, which is also available for you to download and try. So I will start with the curves. So going from regular nodes from Mare Nostrum, so the curves are here, I can drag and drop them here. So we see the curves. And now the HiMem curves. Here. So this first family of curves that we have here are my baseline. So these are my family of curves are my baseline, and this other one is the target. So this is the first input of PROFET, and the second one, the configuration, the CPU parameters. So I have here configuration for Sci-Fi Rapids, which is the one we have in Mare Nostrum. Yeah. And you can see them here. So you have instructions, the reorder buffer size, IPC max, the latency of the last level cache. The parameters are here. And now what we miss is the application profiling. So now let's see the application profiling. So we will start with the Google multi-chase, which is in the beginning of the curve. And we will see in these two families of curves if the performance will change or not. So since they are here, we'll see how much it will change, if it will change or not. So multi-chase here, we just drop the trace here, and we see the application profiled on my baseline system. So this was profiled, it was measured on hardware, and the dots we are seeing here are predicted. So I predict the position of the dots here. And also you see the IPC change. IPC here is performance. So instructions per cycle, we are talking about performance. And we see the decrease in minus 1.4%. So we are talking about 1%, which is almost nothing, because the lead-off latency of the curves are very similar. But now, let's go to our application that is in the end of the curve. And since you see that for these two family of curves, we see the increment in performance, increment in bandwidth. So you have here going up to 150 something. And here in the target curves, we have 20% more bandwidth. So now let's see the impact of this. Since we know that we have this feeling of, okay, it will be in the end of the curve, so it should impact more my performance, right? And let's see if this is true or not. So now here. So we see the application profiled on my baseline system and predict on the target. So you can see the dots moving, going more to the end of the curve here. You can see them moving and using more bandwidth. And now, if I remove, you see here the performance increment. So we increase it by 20% the bandwidth, and we predict increasing performance of 18%. So this is something you can get using high man nodes in Mariana, for example. And also you can use PROFET if you have all the data in normal nodes of Mariana. You can predict where, if it's worth asking for a node with high man, which we know can take some time to get them. You can see if it's worth running your application on this different node or not, based on where your application is on the curves, how much would your performance change. And now the last example. I will erase everything so we don't get confused with data here. I will show how much could my performance application change if we use the MRDIMMs. So we are talking about that technology that increased the bandwidth a lot, and let's see how much we can get, how much my performance will change if I plug a new memory technology, if I plug a MRDIMM to my server. So let's go again. Now we will have different families of curves because we are talking about a different server. We are not talking about Mariana anymore. So we will have RDIMMs as my baseline and MRDIMMs as my target family of curves. So here I have both curves side by side. You can see the bandwidth increase, the latency is almost the same. In the beginning of the curve, the latency is almost the same, but we see this bandwidth increment. Apart from the curves, we need the configuration, which for this system is different than Mariana because Mariana was Sci-Fi Rapids, and this one we are talking about Granite Rapids. So the configuration is different. So let me go down to the configuration. And Granite Rapids, loading the configuration. And now let's see the performance of my applications. So we have here the same applications. Multi-chase in the beginning of the curve, and stream triad in the end of the curve. Does anyone want to bet on the performance of multi-chase? It will going to increase. No? The same? Let's see. So position is okay. We know it's in the beginning of the curve. In the target system, it's in the beginning of the curve. And now let's see the performance. And we have an increase of 90% in this case because the latency is not the same. It's slightly lower. So we measured a slightly lower latency. So in this case, we have an increase in performance too, because if you decrease the latency, you increase your performance. And now let's go to an easier example. So we have application in the end of the curve, and I increase my bandwidth. Would my performance increase or not? Yes? Yes, by how? What would you expect? Like 10%? More than 10%? We increased the bandwidth by a lot.
30.
30. Let's see. 50. Let's go. We have an increase of 38% of my performance. So we see the dots. So we can see them moving in this new family of curves. And we also predict this 38% more performance in my application. And 38%, come on, it's a lot of increment. So that's the demo. So if you want to use it, it's just a matter of having the inputs in the same format. You can adapt for your system, your application, and you can use this to visualize the dots, to predict performance, to see if it worked running your application on a different node, for example, on a different system. So that was the demo, and now going back to the slides. The last thing are some links that you can check if you want to check more. So we have the paper, the GitHub, Claudia work is also here for the sensitivity analysis if you want to do this type of analysis of changing the curve for more latency, less latency, more bandwidth, and also more material here. And that was my last slide. Any questions, comments?